Evaluating composition for discrete sets. Hello everyone. Let's begin by looking at our first slide. To start, let's recall that in the previous subsection, we established the theoretical definition of the composition of functions, focusing on the abstract concept of how one function can be applied to the result of another. Now, we are shifting our focus to a more practical application. When we deal with functions defined over discrete sets, which are simply sets where each element is isolated and distinct, rather than a continuous range of numbers, the process of composition becomes a concrete mapping exercise. In other words, instead of manipulating complex algebraic formulas or equations, we will simply be tracking the movement of individual elements as they travel from one set to another. As we move through the next few slides, I will show you exactly how to trace these paths and evaluate these compositions step by step. Understanding the concept. Now that we have established the theoretical background, let's move on to understanding the actual concept of how this works in practice. When we evaluate the composition of G circle F for discrete sets, you can think of it as creating a bridge. This bridge allows us to connect the starting point, which is the domain of the first function, directly to the final destination, which is the codomain of the second function. To visualize this, let's consider three separate sets: set A, set B, and set C. First, let's define function f. Function f maps elements from set A to set B. This means it takes an input from set A and assigns it to a corresponding value in set B. Next, we have function G. Function G takes over where the first function left off, mapping elements from set B to set C. When we combine these two, we create the composite function, G circle F. This composite function acts as a direct map, taking us from set A straight to set C. Now, pay close attention to the rule for evaluation. To find the image of an element X belonging to set A under the composition G circle F, you must first find the image of X under function f. Once you have that result, you use it as the input for function G. Mathematically, we express this relationship as the composition of G circle F of X equals G of F of X. This notation is simply a reminder to evaluate the inner function first before applying the outer function. In the next slide, we will break this down into a manageable, step-by-step process to ensure you can calculate these values accurately. Step-by-step evaluation process. Now that we have established the theoretical bridge between our sets, let's break down the actual process of evaluation. To determine the values of a composed function when working with discrete sets, you can follow these four manageable steps. First, we begin with step 1, identify the input. Simply select an element, which we will call X, from the domain of the first function, f, which is located in set A. Once you have your input, move to step 2. Apply the first function, f. Your goal here is to find the image of X under the function f. Let's call this intermediate result Y. In other words, f of X equals Y, and this value Y now belongs to set B. Now we move to step 3. Apply the second function, G. Take that result, Y, from the previous step, and use it as the new input for function G. Find the image of Y under G. This gives us a final result, Z, where Z is an element of set C. Finally, we reach step 4, record the final mapping. This final result, Z, is the image of our original input, X, under the composite function, G circle F. Therefore, we can formally state that G circle F of X equals Z. By following this sequence, you have successfully mapped an element from the first set all the way to the third. In the next few slides, we will apply these exact steps to a real-world logistics example and a mathematical problem to see this process in action. Real-world example, the logistics chain. Now that we have established the theoretical steps for evaluating compositions, let us apply these concepts to a real-world scenario to make the process more intuitive. Imagine a simplified logistics chain within a company. First, let us define our three discrete sets. Set A represents our orders, which contains order 1, order 2, and order 3. Set B represents the warehouses, consisting of warehouse alpha and warehouse beta. Finally, set C represents the delivery trucks, which are truck X and truck Y. Next, we define the functions that connect these sets. Function F is the process of assigning an order to a warehouse. In this case, order 1 is mapped to warehouse alpha, order 2 is mapped to warehouse beta, and order 3 is also mapped to warehouse alpha. Then we have function G, which assigns a warehouse to a specific delivery truck. Here, warehouse alpha is mapped to truck X, and warehouse beta is mapped to truck Y. Now, let us evaluate the composition, denoted as G circle F. The goal here is to create a direct mapping from the original order in set A to the final truck in set C. For order 1, we first apply function F, which tells us it goes to warehouse alpha. We then use that result as the input for function G, and since warehouse alpha maps to truck X, the final result is that the composition of G circle F of order 1 equals truck X. Moving to order 2, function F maps it to warehouse beta. We then apply function G to warehouse beta, which leads us to truck Y. Therefore, the composition of G circle F of order 2 equals truck Y. Finally, for order 3, function F maps it to warehouse alpha. Applying function G to warehouse alpha again leads us to truck X. Thus, the composition of G circle F of order 3 equals truck X. As you can see, we have successfully bridged the gap from orders to trucks by using the warehouse as an intermediate step. In the next slide, we will apply this exact same logic to a purely mathematical example using numbers and variables. Mathematical example. Now that we have seen how this works in a real-world logistics scenario, let us apply the same logic to a purely mathematical example to solidify your understanding. First, let us define our three sets. We have set A, which contains the elements 1, 2, and 3, set B, which contains the letters P, Q, and R, and set C, which contains the capital letters X, Y, and Z. Our functions are provided here as sets of ordered pairs. Function F maps 1 to P, 2 to Q, and 3 to R. Meanwhile, function G maps P to X, Q to X, and R to Y. Our goal is to find the composite function, G circle F, as we established in the previous slides. This means we are creating a direct map from set A to set C by using set B as our bridge. Let us perform the step-by-step calculation. Starting with the first element of set A, which is 1. First, we apply function ff of 1 equals P. Now, we take that result, P, and use it as the input for function G of P equals X. Therefore, the composite value, G circle F of 1, is X. Next, let us look at the element 2. Applying the first function, f of 2 equals Q, we then take Q and plug it into function G of Q equals X, so G circle F of 2 is also X. Finally, for the element 3, f of 3 equals R. Then, we find the image of R under function G, and G of R equals Y. This gives us the result that G circle F of 3 is Y. To conclude, we can now express the final composite function as a set of ordered pairs. The mapping is 1 maps to X, 2 maps to X, and 3 maps to Y. Pay close attention to the order of operations we used here, as the next slide will cover some common mistakes students make, such as reversing the order of the functions. Common mistakes. Now that we have walked through the logistics chain and the mathematical example, it is important to address some common pitfalls. Let's look at the most frequent mistakes students make when evaluating compositions. First, be very careful about reversing the order of operations. A common error is applying function G first and then function F. To avoid this, always look at the notation. G circle F of X, the function closest to the variable X, is the one that must be applied first. In this case, you must evaluate f of X before you can use that result to evaluate G. Secondly, avoid the temptation to ignore the intermediate set. Some students try to jump directly from set A to set C, skipping the middle step. Remember the bridge concept we discussed earlier. You must always ensure that the output of function f is a valid input for function G if f of x results in a value that is not present in the domain of G, then the composition is simply not defined for that specific x. Finally, let's clarify a point on notation. Do not confuse G circle f of x with the algebraic product of g of x multiplied by f of x. Composition is a nesting of functions, where one is placed inside the other, not a multiplication of their individual values. Keep these points in mind as we move toward our final summary and key takeaways in the next slide. Key takeaways. To wrap everything up, let's go over the key takeaways from this lesson to ensure you have a solid grasp of evaluating compositions for discrete sets. First, let's recap the concept of sequential mapping. As we saw in both our logistics and mathematical examples, composition for discrete sets is essentially a two-step process. We move from set A to set B using function f, and then from set B to set C using function g. This leads us to the core logic, often referred to as the chain rule in this context. The most important thing to remember is that the output of the inner function, f, becomes the immediate input for the outer function, g. It is a seamless handoff between the two functions. Now, let's clarify the notation one more time to avoid the common mistakes we discussed. When you see the expression g circle f of x, it is read as g circle f of x, and it is mathematically equivalent to writing g of f of x. Just remember to always evaluate the inner function first. Finally, let's define the boundaries of this process. The domain of the composite function, g circle f, is the domain of the first function, f, and the final codomain is the codomain of the second function, g. In simpler terms, the entire process starts with an element from set A and ends with a result in set C.